Okay, hello everyone. My name is Vivek. I'm a graduate student at UC Berkeley. I'm happy to be presenting some work. This is joint work with Aydın Buluç and Demmel on distributed memory sparse kernels for machine learning. So we'll be talking about two sparse kernels today. These are sample dense matrix multiplication and sparse times dense matrix multiplication. And these two kernels appear in a bunch of diverse applications. These include self-attention-based graph neural networks, collaborative filtering problems. These are Netflix challenge type matrix factorization applications, and document clustering. And both of these kernels are sort of the two natural operations you can do when you have a single sparse matrix and two dense matrices, typically tall, skinny. And usually an application will use the output of the SDDMM operation as the input for SpMM and use both operations in sequence. And when the sparse matrix is the adjacency matrix of a graph, we have very specific interpretation for these kernels. That is that sample dense matrix multiplication generates a message on each edge of the graph, and SpMM aggregates these messages from the edges to their incident vertices. There's been lots of existing work on these two kernels. So in the shared memory space, we have a bunch of works that perform blocking to improve cache efficiency, sparsity-aware reordering of the sparse matrix, tuning the tile shapes that you use for cache blocking, and even fusing the SDDMM and SpMM functions. Now, in the distributed memory space, we have lots of distributed memory algorithms, 1.5D algorithms, so-called 2.5D algorithms for sparse times dense matrix multiplication. We have some applications for these, such as large distributed graph neural networks. And in addition, we have some works that treat these kernels using one-sided communication. Now, in the landscape of distributed memory dense linear algebra, we have these 2.5D algorithms that take advantage of extra memory on your cluster. And recently, there was this work called COSMA that was proposed. This generates tight I/O schedules for matrix multiplication, where the matrices have irregular sizes. There's been really not much work at all on distributed memory, sample dense matrix multiplication, and FusedMM, and that's what we aim to tackle. So our contributions are, we're going to give the first distributed memory implementation of sample dense matrix multiplication, and we're going to do it by adapting existing communication avoiding algorithms for SpMM that exist in the literature. And our implementations can scale and take advantage of extra memory on the cluster by replicating inputs and outputs. Furthermore, when you execute an SDDMM followed by an SpMM, we're going to give some strategies to cut down the communication costs. We both eliminate unnecessary rounds of communication, and we're going to change the optimal replication factor. And finally, we're going to benchmark our algorithms both within real-world applications and on Erdos-Renyi random matrices on billion-scale real-world matrices. Okay, so let's talk about designing distributed memory SDDMM algorithms. I'm going to use the following notation. So S and R here are m by n sparse matrices. A and B are m by R and n by R, respectively, dense matrices. I'm going to define this ratio of phi as the ratio of the number of non-zeros in my sparse matrix S to the total number of entries in dense matrix B at n R. I'm going to use star to denote element-wise multiplication and a dot for matrix multiplication. And now let's actually define these two kernels. So given these two dense matrices A and B and a sparse matrix S, sample dense matrix multiplication computes the element-wise product of S with A times B transpose. Here's a little pictorial depiction of this. We have A times B transpose, that's a matrix multiplication, followed by a mask where the mask entries are given by S. So the output clearly has non-zero locations identical to S. And I'm going to distinguish between the SpMM operation that multiplies S and A and the operation that multiplies S transpose and B. The reason we're going to do this is that several applications that we're going to see, such as graph neural networks and collaborative filtering, require both of these operations alternately. So I'm going to define SpMM A and SpMM B as follows. SpMM A multiplies S times B, and SpMM B multiplies S transpose times A. So the suffix of A or B refers to the shape of the output generated by each kernel. Now, finally, as I mentioned before, applications typically make a call to SDDMM to generate messages and then immediately aggregate these messages using an SpMM operation. So I'm going to define FusedMM A and FusedMM B as compositions of SDDMM with these two kernels. Okay, so let's talk about what what sparsity-agnostic distributed SpMM means, which is the type of algorithm that we consider in our work. Sparsity-agnostic algorithms operate similarly to the canon and summa dense linear algebra algorithms. They shift large blocks of A, B, and S, interleaved with local computation. And these algorithms don't really benefit from graph partitioning. They rather rely on a random permutation of the rows and columns of S to ensure load balance among the processors. And we characterize such algorithms as 1.5D or 2.5D or 2D, depending on which submatrices they replicate, propagate, and keep stationary. So given all this, how do we take an algorithm for SpMM and convert it to an algorithm for sample dense matrix multiplication? Well, let's first observe that these two kernels have identical data access patterns. If we look at the serial algorithms to compute SDDMM and let's say SpMM-A, for SDDMM, to compute the Rij entry of the output, you take the weighted, you weight the dot product of the ith row of A and the jth row of B by the coefficient Sij. To compute SpMM-A, on the other hand, you take the you weight the jth row of B by the coefficient Sij and accumulate it into the ith row of A. So we can see from this that every non-zero of the sparse matrix requires this interaction between a row of A and a row of B, which leads us to the following assertion, that every distributed memory algorithm for SpMM can be converted into an algorithm for SDDMM that has identical communication characteristics. And you can go back and forth between these, convert an SDDMM algorithm back to an SpMM algorithm. Okay, so how exactly do we do this? Well, let's first consider any distributed algorithm for SpMM-A that performs no replication, and we'll add in replication in just a second. So for any index k in the range 1 through r, at some point in its execution, the algorithm has to collocate these three coefficients, Sij, Aik, and Bjk, on one processor. And then it has to perform this local update, Aik plus equals Sij, Bjk. Now I'm going to transform this algorithm as follows. I'm going to change the input sparse matrix S to an output that is initially 0. I'm going to change A from an input to an output. And then I'm going to change the local update into Sij plus equals Aik times Bjk. Now, if you stare at this algorithm, you'll see that this transformed procedure performs sample dense matrix multiplication up to the multiplication with the original values of S, which can be taken care of as a post-processing step with no additional communication. And the communication characteristics of this algorithm are identical to my original SpMM. Now, this isn't the full story. 1.5D and 2.5D SpMM algorithms, they replicate the input and output matrices to reduce communication bandwidth. And they use extra memory in the process. Now, inputs are typically replicated through a broadcast at the beginning of the algorithm. And if we replicate an output, we're going to need a reduction to sum up any temporary accumulation buffers. So I'm going to extend the transformation procedure as follows. I'm going to replace initial broadcasts of any input buffers with terminal reductions, and replace the terminal reductions with initial broadcasts. This completes the transformation, and we've given a way to convert between algorithms for SDDMM and SpMM. Now let's talk about strategies to reduce communication when you execute both kernels, one right after the other. So let's consider the FusedMM-A operation. So the simplest distributed implementation for this is just going to execute the SDDMM and just feed the intermediate result to SpMM. And we're taking advantage of the fact here that we have identical input and output data layouts for both of these kernels, so we don't have to do any reorganization of A, B, and S in the process. Now, we're still performing replication and propagation for both SDDMM and SpMM. So if you look at kind of the flow chart of operations that happen here, you'll notice some redundancies. There's an initial broadcast followed by some local computations, moving data in a loop, followed by some reduction of any replicated outputs. We have another broadcast if we replicate any inputs for SpMM, followed by a local SpMM and a loop of moving data. And finally, if we replicated any outputs in the second phase, we need to reduce them. And finally, our algorithm is complete. So we can simplify this in one of two ways. And the first way that we're going to consider is called replication reuse. So replication reuse reuses the replication of the same dense input matrix for both SDDMM and SpMM. And this allows us to do two things. First, we are cutting out some unnecessary rounds of communication. Notice that we only have a single broadcast of a common dense input at the beginning. And second, we can actually save some communication by increasing the replication factor relative to the unoptimized sequence. Notice that the ratio of broadcast to date of movement, that's the yellow blocks in this flowchart here, has decreased, so I can afford to increase my replication factor. The second strategy that we're going to consider is called local kernel fusion. So instead of having two phases of local computation followed by moving data, I'm going to combine those two phases into one. So local kernel fusion executes a local SDDMM and SpMM on each processor without any intermediate communication. Now, the price we pay for this is that if we broadcast a dense input to replicate at the beginning, we also need to perform a reduction at the end for replicated output. Nonetheless, this strategy is useful, not only because it, again, cuts out unnecessary communication rounds, but we can also decrease the optimal replication factor compared to the unoptimized sequence. And the caveat here is that we can't apply local kernel fusion to any algorithm that splits the dense matrices by columns among processors. The reason for this is that message generation has to precede aggregation. We can't begin SpMM with partial results on the edges, which occurs for any algorithm that divides these dense matrices by columns among different processors. Nonetheless, both of these strategies are useful. Now let's take a look at how exactly we design our algorithms and how exactly we move data and perform local computation. So we're going to design our algorithms by deciding which matrices we're going to replicate, propagate, and keep stationary. Now, for the sake of our communication analysis, I'm going to assume that M is approximately equal to N. So these are roughly square-shaped sparse matrices, which arises in a lot of graph applications. And these choices just affect the communication complexity of each algorithm. So we're going to see that the optimal choice of algorithms can depend on the ratio between the non-zero count of the sparse matrix and the total entries in either dense matrix, which is that ratio of phi that I defined earlier. And we're really going to be looking in this red box here to see, how the choices of replication, propagation, and which matrices to keep stationary affect the communication costs. So here are our choices. We choose to replicate only a single matrix. We can choose either the dense matrix or the sparse matrix. If we choose to replicate the dense matrix, we can choose to propagate both the dense matrix and the sparse matrix. This really leads to a 2.5D dense replicating algorithm, or we can choose to propagate either the dense matrix only or the sparse matrix only, which leads to 1.5D dense shifting and 1.5D sparse shifting algorithms, respectively. On the other hand, if we choose to replicate a sparse matrix, you can choose to propagate both dense matrices. That's a 2.5D sparse replicating algorithm. Or if we choose to propagate only a single dense matrix, you get what we call 1.5D dense shift and sparse replicate. We don't consider this algorithm because its properties in theory are strictly inferior to the 2.5D sparse replicating algorithm. Now, for our 1.5D algorithms, again, we have two variants. You can either cyclically shift the dense matrix between rounds of local computation and keep the sparse matrix stationary, or you can cyclically shift the sparse matrix and keep the dense matrix stationary. And this choice just affects the number of words that you communicate. For the dense shifting algorithm, you have this NR over P to the 1/2 number of words communicated at max by any one processor. And the sparse shift, you have the same asymptotic complexity, except you've got this factor phi to the 1/2 in the numerator. So again, the value of phi is going to determine which of these two algorithms is optimal. For our 2.5D algorithms, again, we have two variants, and both of these shift at least one dense matrix. Given that we are shifting at least one dense matrix, you can choose to replicate one dense matrix and cyclically shift the other. And you can also choose to replicate the sparse matrix and cyclically shift both dense matrices. Now, if you look at the number of words communicated for our 2.5D algorithms, you'll notice that they're very similar to our complexity for the 1.5D case. So you've got this P to the 2/3 in the denominator. And for the dense replicating algorithm, you have phi to the 2/3 in the numerator. For the sparse replicating algorithm, we have phi to the 1/3. And again, the value of phi and the number of processors you have determines which of these algorithms is optimal. Now, our predictions are that when phi, the ratio of the number of non-zeros of S to NR, is low, communicating the sparse matrix is cheaper. So our 1.5D sparse shifting algorithms and sparse replicating algorithms are going to win out. Now, on the other hand, when phi is high, communicating the dense matrix is cheaper. So the 1.5D dense shifting and 2.5D dense replicating algorithms should perform faster. Now, for the range of processor counts we consider, we predict that 1.5D algorithms should usually outperform their 2.5D counterparts. And finally, we predict that communication elision should save around 30% of communication for 1.5D algorithms and 20% of overall communication for 2.5D algorithms. Okay, let me talk about some of our experimental results. So we ran our experiments on Cori, which is a Cray XC40 at Lawrence Berkeley. We ran our experiments on 256 Knights Landing cores, Knights Landing nodes, excuse me. Each node has 68 cores running at 1.4 gigahertz. All nodes are connected using this Aries Dragonfly topology, and we use this hybrid MPI and OpenMP programming model with a single MPI rank and 68 threads per node. The first thing I'm going to demonstrate is the effect of this ratio phi. So for m equals n is 2 to the 22 and 32 processors, I'm going to vary the non-zero count per row of S to affect the density of my sparse matrix. And the column count of my dense matrix, that's that parameter R, determines which of our algorithms perform best in a variety of situations. And you can see here that as we predict, we see that the 1.5D algorithms generally beat their 2.5D counterparts. And the choice of either 1.5D dense shifting or sparse shifting depends on the value of the ratio phi. When phi is below this line, which is phi equals 1/3, you'll see that the 1.5D sparse shifting algorithm is winning out, and otherwise the dense shifting algorithm is winning. We have excellent agreement between our prediction and what we observe. To test strong scaling, we compare our FusedMM implementations against 2 repeated calls of SpMM from the PETSI library. There's no good existing distributed implementation of SDDMM to compare against. Now, PETSI only supports 1D partitions of all matrices and does not take advantage of replication. So this is going to lead to poor scaling when you have a high number of processors. So we tested on several matrices from sweet sparse and one significantly denser matrix from computational biology. That's that eukarya matrix here in the middle of the table with 111 non-zeros per row. R equals 128 for all experiments. And here are our results. I'll just highlight a few curves from this set of plots. So the black curve that you see on top, this is our baseline comparison of PET-C. You can see that PET-C very quickly exhibits poor scaling at high processor counts. The red curves here are 1.5D sparse shifting algorithms employing replication reuse. So these by far have the best time when the sparse matrix has relatively few non-zeros compared to the total number of entries in the dense matrix. And we see this for the Amazon and UK matrices. On the other hand, the significantly denser eukarya matrix exhibits the 1.5D dense shifting algorithm with local kernel fusion performing the best. And we see a similar story for the Twitter 7 matrix, which is the largest test case, where the 1.5D dense shifting algorithm wins out. Here we plot the predicted versus observed optimal replication factors, and we notice excellent agreement between what we predict and what we observe. Now, our predicted replication factors are overestimates in some cases over the true observed optimal replication factor for some processor counts. And the reason is that we found is that the broadcast collective across fibers of our processor grid was more expensive than the cyclic shifts, which affects the communication dynamics in a way that our model could be easily modified to capture, but doesn't, leading to some overestimates of the optimal replication factor. Now, to test weak scaling, we examine the behavior when we keep the flops per processor constant. We use 2 setups. The first setup, we're going to double the processor count for each successive experiment, and double the side length of the sparse matrix from experiment to experiment, and the non-zero count per row of the sparse matrix remains constant at 32, as well as does the embedding dimension R constant at 256. So when you perform this experiment, you'll notice a couple things. You'll notice that the ratio phi equals number of non-zeros of S over NR remains constant, but the fraction of non-zeros in the sparse matrix is successfully decaying by a factor of 2. In this case, we expect p to the 1/2 communication scaling from our 1.5D algorithms and p to the 1/3 scaling for our 2.5D algorithms. And here are our results. Because of the fact that we have this rapidly decaying fraction of non-zeros in the sparse matrix, the sparse matrix very quickly becomes lighter and easier to move than the dense matrices. So as predicted, our 1.5D sparse shifting algorithms win out. That's that red curve you see at the bottom of the figure. Likewise, our 2.5D sparse replicating algorithms win out among 2.5D algorithms. In addition, we can see from these plots that both local kernel fusion and replication reuse yield communication savings, and local kernel fusion tends to outperform replication reuse. In addition, we're going to benchmark the breakdown of time spent in replication, propagation, and computation for our algorithms. And you'll notice here that all of our algorithms successfully leverage replication to drive down the cost of propagation, especially as the processor count increases. In all of our experiments, computation is generally the lower order term. These are heavily compute-bound kernels. We test an alternate method of weak scaling. In each successive experiment, we're going to quadruple the processor count. We're going to double the side length of the sparse matrix. And the non-zero count per row of the sparse matrix is also going to double with an initial value of 32. And we're going to keep a constant embedding dimension for rows and columns. Now you'll notice here that the ratio phi successively doubles, while the fraction of non-zeros in the sparse matrix remains constant from experiment to experiment. And in this situation, we expect communication to stay constant for 1.5D algorithms and even decrease slightly for 2.5D algorithms. Due to decreasing node locality, this is highly unlikely in practice. But here are the results. You'll notice that the y-axis for the weak scaling setup 2 tops out at about 5 seconds, where it was close to 25 seconds for weak scaling setup 1. And here we see the exact opposite story. We see the 1.5D dense shifting algorithms winning out precisely because it is successively more difficult to shift the sparse matrix. And finally, the communication costs of the 1.5D algorithm don't depend on this value phi, which is successfully doubling, affecting the performance of our 1.5D sparse shifting algorithms, yielding better scaling overall. Finally, let's get to some application benchmarks. The first benchmark we try is collaborative filtering. So this is a Netflix challenge type computation where we want to compute a low rank factorization of a sparse matrix S equals A times B transpose, where A and B are tall skinny embedding matrices. Now, the key here is we want to minimize the squared error norm only on the non-zero entries of S. We don't care about the zero entries. And what this leads to is an individual least squares problem for every row of the unfixed matrix. We're going to alternately optimize either A or B, keeping the other matrix fixed. And we have this independent least squares problem for every row of the unfixed matrix. And the solution to solve all of these systems in parallel is to use a Krylov method. We're going to use conjugate gradients, and we're going to use SDDMM and SpMM to compute all the query vectors at once in parallel at each stage of conjugate gradients. The second application that we tried was a graph neural network with self-attention. So graph neural networks learn embeddings for each node of a graph. The key operation is graph convolution, which is this aggregation primitive that is exactly SpMM. And a single head graph attention network weights each edge by some function of the incident vertex embeddings. So these edge weights become coefficients in the aggregation, and you'll notice that this is just a modified sample dense matrix multiplication. A multi-head graph attention network concatenates the outputs of single heads, and we perform message generation and aggregation using SDDMM and SpMM. So here is the performance breakdown for our algorithms. We run 20 iterations of ALS and benchmark the performance and breakdown, as well as a toy graph attention network with random weight matrices to test the scaling performance. So you'll see here that the time breakdowns and the overall results match those of our strong scaling experiments. We see that for the Amazon matrix, the 1.5D sparse shifting algorithm is winning out. We see that all of our algorithms can leverage replication to drive down the cost of propagation, and computation in both FusedMM and outside is sort of a lower order term. These applications are again heavily communication bound. So in summary, we gave a theoretical communication analysis of Sparsity-Agnostic communication avoiding SDDMM and SpMM algorithms, and then gave some strategies to execute FusedMM by eliding communication between both of these kernels executed in sequence. Furthermore, our algorithms can take advantage of replication, scaling to extra memory on the cluster with hundreds of nodes and thousands of cores. And finally, we tested our algorithms within 2 applications that make use of FusedMM. Now, future work would involve more effective communication computation overlap, as well as implementations with something like one-sided MPI or remote direct memory access, as well as porting our implementation to GPUs, which have higher computational throughput. Thank you very much, and take a look at our paper if you're interested in more.